Hello everybody and welcome back. So in this next segment of our Chapter 4 discussion, we're going to talk about the discrete probability distribution called a binomial probability distribution, which is a very important one to us. And it's a very specialized kind of distribution, and the way it works is this. Let's say that we conduct a binomial probability experiment. For example, a toss of a coin is a binomial random experiment. We say that if we get heads, right, that's our success. If we get tails, that's not success. So that's what we have. In a binomial probability experiment, the same action is repeated a fixed number of times, and each trial is independent of the others. And there are only two outcomes of interest. Either we have success or failure, as we define it in terms of that experiment. So there's only two outcomes right here. So we're going to define the following quantities. Let n be the number of trials, x be the number of successes within those n trials, let p be the probability of success in each particular trial, and of course q would be the probability of failure. So we could say that q is the complement of p. In our notation, we use this x, little squirrely little symbol right there. X is read as the binomial distribution with regard to n, the number of trials, and p, the probability of success. Now there is a probability formula that involves something called a combinations. We're going to use Excel to work out everything that this formula would tell us. So that's where I've got these two formulas up the front. Either we use it as cumulative or as a not cumulative distribution, and we'll take a look at both of those right here. So let's go to our example on Excel and check this out. Let's say that we've got a test consisting of 50 multiple choice questions, and each question has 3 possible answers. Which one of the following is correct? So we want to see, let's assume one of which is correct, right? So we're going to assume that we don't know any of these answers. We're just simply going to guess those answers, right? Well, what should we be able to say about our probability within this? Well, okay. Let's talk about this. We said our number of trials. Well, even though there's 50 questions in this test, we're only guessing the first 7. So we're going to use n equals 7 for our experiment in this case. What's the probability of success for each trial? Well, if we're simply guessing out of 3 letters, A, B, and C, we're going to say our probability is 1/3. Okay? So that's the number that we're going to want to choose. Now, whether we want cumulative as true or false, that's going to depend on what the wording is. So we'll look at those wordings right here. So let's say that we're asked to find out of those 7 guesses, what's the probability of getting exactly 3 correct? Well, in this case, we do not want a cumulative, so we're going to use false for cumulative because we only want the probability of that one single exact number of successes. So in this particular case, we're going to use x equals 3 as our number of successes out of those 7 trials. What's our probability? Well, here's what we do. We type in the command binom.dist, and we see that pops up as one of our formulas. We're going to type in the number x trials of number of successes, the number of trials, of which we said was 7. Our probability was 1/3. We can actually enter in 1 divided by 3 if we happen to know that, or we could have entered that in as a decimal. And we're going to choose false because we want the probability mass function. That is, we want the probability at exactly 3. So we're going to have to enter in 3 right here for x, and let's see what happens. There we go. All right, so the probability of getting exactly 3 out of the 7 correct is about 25.61% right here, I would say, 0.25606. All right, of those 7 guesses, what's the probability of getting at least 3 correct? Well, there's a couple of ways of putting this, but right here in this case, this is going to be a cumulative probability. And the way we're going to think about this is that if we want the probability, because we're using Excel, we have to do it this way. The probability of getting greater than 3, right, at least 3, is going to be equal to 1 minus the probability of getting x less than or equal to 3? Correct. So in other words, we're going to have to subtract this value from 1 in order to get the probability that it's greater. So here's the way we're going to work this one. We're going to say equals 1 minus the binom.dist, right? Here's our formula. We want getting at least 3 correct, right? So we're going to use at most 2, really, in this case. Our number of trials remains 7. The probability within each trial of success is 1/3. And the cumulative probability is the one that we want, so this time we choose true. And then we type that in. All right, so the probability of getting at least 3 correct is 0.42936. And what this is the same is if we added up each of the probabilities one by one for getting 3, 4, 5, 6, or 7 guesses correct. And we could verify that if we actually work this one through. If we put, let's see, 3, 4, 5, 6, or 7 as our number of trials or as our number of successes, and we just did the binomial probability for each of these. So I'm going to do that real quick just so that you see it in action. Number of trials correct out of 7 with a 1/3 probability of success, and this time false here because I'm getting a single probability. Just notice that was the one that we got before for 3, and then we take all of these probabilities and we get their sum. Since each trial is independent, remember we can use the addition rule, and our addition is the sum of each of these. Right? So rather than having to do that several times, we can just simply use true at the end of our statement with this binomial distribution. Okay, a couple of quick notes about the binomial. Our mean is very easy to find. Our mean probability is going to be equal to the number of trials times the probability of getting it correct in each guess. So in this case, here's what we're going to do. Now let's say that we've got a test that consists of those 50 multiple choice questions again. This time, we've got 5 possible answers, A, B, C, D, and E, right? One of which is correct. Assume you guessed the answers to the first 10 questions, all right? So now in this case, we're going to let n equal 7. So we're going to let n equal 10, right? Because that's the number of our trials. And this time our probability is equal to 1/5. All right. So what should we say? Well, our mean probability is simply going to be equal to 10 times 1/5, which is to say 2. We would expect on average to have 2 guesses out of those 10 correct. What is the variance? Well, the variance is the number of trials times our probability of success times our probability of failure. What's our probability of failure? Well, Q is always equal to 1 minus P. And in this case, that's equal to 4/5. All right, so let's see what that looks like. We're going to get 10 times 1/5 times 4/5, giving us a variance of 1.6. And of course, if we take the square root of that number, we've got our standard deviation. So in this case, 1.26. Well, let's just try this one more time, right? Because when we think about why casinos do really, really well, it's not because the probability of them winning is any better than your probability of winning any particular game. The reason why casinos do well is because they have an expected value that happens to be higher than yours. Let's just illustrate this point right here. Let's say you place a bet on a number 7 in roulette, and you have a 1/38th probability of winning. So what's the mean and standard deviation for the wins of people who bet on the 7 50 times? Well, the mean is going to be 50 times 1/38th. All right, so what we're going to do is we're just going to go ahead and multiply those two. Equals 50 times 1/38th, Right? Let's see what happens right there. 1.315. So if you bet it 50 times, you should expect a winning of about 1 to 1.3 times out of that, right? What's the standard deviation of that? Well, our standard deviation will be the square root of the number of trials. So we are going to do 50 trials, right, times our probability of winning, which is 1 out of 38, times our probability of not winning, which is going to be 37 out of 38. What do we get now? 1.13. Isn't that interesting? Well, in this case, our probability is going to be pretty close to our mean, right? Which means that on average, we would expect to go anywhere from 0 to maybe 2.5 times winning out of 50. Think about the casino on the other end of that. They're doing pretty well. Okay. Well, that's our binomial distribution, right? Here we go, just exactly what we said, right? And of course, these are our mean, standard deviation, and variance formulas right here. Next up is our Poisson distribution, so stand by for that.